I'm going to go quickly through a few slides here that relate to some of the things you've heard from other speakers. In particular, the RBMs and the regular kinds of RBMs that you've seen and the autoencoders have the property that the inference, in other words, computing the features or computing the internal representations is very easy and cheap, but on the other hand, they don't have explaining away. So in other words, they don't have any competition between the causes. And there's an interesting piece of work from Adam Coates and Andrew Ng that I guess Andrew may have mentioned last week, which shows that this explaining away, this competition could be a really important part of the puzzle. In particular, if you train the filters as RBMs and then you actually use those as if they were trained from sparse coding, and you continue doing the decoding using the sparse coding explaining away, you get better classification error. That suggests that this competition between filters, between features, is something that may be useful, that we don't have in regular RBMs or regular autoencoders. But in both cases, you could easily think of ways to fix that by adding lateral connections between the hidden units.
Then there is the opposite result from people in Switzerland and Italy that says that you train a sparse coding and then you use the basis functions as filters and it works just fine. You don't need to do explaining away.
Okay, so who's right?
Who's right? Yeah, we don't know.
Okay, I don't know. See, that's why we need more experiments and more understanding. So sparse coding, you've seen that. I'm going to skip. Predictive sparse decomposition, I assume Jan told you a lot about already. And now let me say a few words about deep variance, because up to now I've been talking about sort of single layer learning, and I've mentioned sort of one sort of generic recipe to get deeper models, but you can have many other variants. One of the reasons we're interested in this single layer learner is because directly training deep models seems much harder from an optimization point of view, and we still have to understand that. One sort of general take-home message from a bunch of different experiments that people have done is that it looks like having some kind of training signal at the level of each level is probably very useful. And there are many ways you can implement that idea. So you've seen how you could stack RBMs or you could stack autoencoders into a deep neural net. Once you've trained the RBMs or once you've trained the autoencoders, you can just take the weights and plug them into your MLP. I guess you've heard that enough. You probably heard how you could take a stack of RBMs or a stack of autoencoders, single layer RBMs or single layer autoencoders, and get a deep autoencoder. So here we take the encoding function of the first RBM or the first autoencoder and you stick it here. Then you have the encoding function of the second one, you stick it here, and the third one you stick it here, and then you take the decoding function of the last one. So now you have encode, decode using the second level decoder, and then decode using the first level decoder. So you have encode, decode, and that logic is meaningful and works. And there was one of the first papers on RBMs by Jeff and Russ Salakutinov. Then there's a thing you didn't hear about because it's in French somewhere. It's the master thesis of one of my students, where basically we explored recurrent autoencoders. And it turns out the construction is very similar to what you find in the way you stack RBMs into deep Boltzmann machines, but consider the deterministic computation. Okay, so we start from a stack of RBMs or stack of autoencoders, and we're going to build this flow graph. So each here, this is time and sort of computation time. And we're going to start with our input. We're going to encode into the first layer, and then we're going to send that to the second layer, but also decode back. And then, you see this graph of basically at each point, at each layer, you have inputs from above and inputs from below. And notice these 1/2s, because whereas in the original model, each layer was only receiving input from either below or above, here they're receiving inputs from both below and above. And this idea of halving the weights is from Russ and Jeff that they use in their deep Boltzmann machine, that we can do the same thing with autoencoders, and you get a kind of recurrent autoencoder. So at every point or every half point, you get a reconstruction, and you can minimize the reconstruction errors either at the end or actually better at every point. And you just do backprop through this whole graph with errors at each of the reconstruction points, and that works, but it's just preliminary, and I think more needs to be done in that for that kind of thing. In particular, I think adding lateral connections, which we haven't done, would be useful. You might as well, if you're going to have sort of iterative recurrent computation, you might as well have lateral connections. So I'm sure Jeff explained how you can stack RBMs to get a deep belief network, and you get this kind of construction where to sample from the model, you do Gibbs sampling on the top level RBM, and then you go down stochastically to generate a new input. And then the deep Boltzmann machine is similar to the one we just did before with the autoencoders, except at each of these steps you stochastically sample in addition to propagating in the same way that I've shown. And you can train the deep Boltzmann machine using the same principle that we can use to train RBMs. I'm sure Jeff, I assume Jeff went through that. Is that correct? Okay, good. Now there's a new thing. Russ will go through that. Okay, good. So that's something Russ won't tell you about, and Jeff either, because we just came out with this at the last ICML 2 weeks ago. I mean, we came out with it a few months ago, but this is where it was published. And you can think of it's something similar to the deep belief net, but in the world of autoencoders. So I'm using the ideas that I sort of outlined in previous slides. We're going to be able to sample from autoencoders. But it turns out that if we have a deep autoencoder, it's much better. And so what we do is we have a stack of autoencoders, and then we sample from the top autoencoder. So now this is stochastic. At each step here, you add noise. And then at the last moment, you just deterministically project back to the input, and you have a generated input. Now I'm going to explain how you sample from an autoencoder. Oh, here's the procedure, basically. You take your previous state, you decode encode, you get a new state, and you add some noise. So this part is deterministic. It corresponds to some kind of reconstruction. And this part, here the noise, you have to be careful about how you choose it. Sigma is some scalar that you control that determines the size of the steps you're making. And the noise is basically a normal zero mean noise with the covariance in the direction of the Jacobian of the autoencoder. Let me explain that a bit more in coming slides. Right, so we're gonna, to construct our sampling algorithm, we are going to exploit our understanding of the geometry that goes with the interpretation of the autoencoder is capturing the local tangent planes. We're going to exploit the fact that the reconstruction points in the direction of high density. So in the algorithm, we actually take a point where we are, we map to a high probability point, basically mapping to the manifold, and then we add some noise which is going to be along the manifold. And basically what that's going to do is walk on the manifold. First go to a manifold and then walk on it. So let's actually do the pictures. So here's some manifold. Of course, life is not as simple as this, as we had in our discussions, but it's visually appealing. We start somewhere. Let's say we already converged. I mean, we already burnt in, so near a high probability region. We add some noise in the directions of the tangent plane. So that's exactly what I said before. Remember, we've found the directions of the large singular the singular vectors corresponding to large singular values, but actually we don't need to even do an explicit an explicit SVD. We can just take the matrix of derivatives directly and use it with symmetrizing it, using it as a covariance matrix. And then we basically add that noise. That may actually move us out of the manifold because it's a linear approximation. And then we project back on the manifold by doing a reconstruction of that. And that's it. We repeat the same procedure again and again, and that moves us along, near the manifold and along the manifold. And if you start from a region which is far from the manifold, because the reconstruction moves you towards the manifold, in one or very few steps, you get on the manifold, and once you're on the manifold, you just walk on it randomly, and you get this random walk. Now, in practice, you don't actually just stay on this nice plane. You have thickness in all directions. You have a Gaussian, which is full rank, but this Gaussian will be very flat in some directions, which are the directions estimated by the model as I showed before. So we've tried this on different data sets. So you get samples using from MNIST here. You get samples from faces. This is a Toronto face database. So this is using a denoising autoencoder as the model. We've also done it with a contractive autoencoder. So these are samples. Okay, wait, top here is using a contractive autoencoder, actually a 2-level one. And this is from a deep belief network, which I think gives slightly better visually. But these are pretty reasonable. And we have a technique to estimate the quality of the samples sort of quantitatively, and essentially it's the same as DBNs. Now this picture here shows what happens if the noise you add at each step is isotropic. Instead of adding noise which is sort of oriented in the directions estimated by the model, if you were just to reconstruct and then add noise sort of in all directions, you wouldn't get very nice samples. You would get things like this or things like this. So let's try to understand better this sampling procedure and see what it means and what is it that's happening. So we've constructed a Markov chain, which is summarized by this equation. So this is the fixed point of the Markov chain. It says that if I start at a point x tilde, what I'm going to do is I'm going to compute two things. I'm going to compute a mu and a sigma for my Gaussian that I'm going to sampling from. And sigma is a matrix, mu is a vector. And then I'm going to sample an x from that Gaussian. And then if the point from which I started was sampled from my distribution pi, and my chain has converged, then at the end, the new x is also from the same distribution pi, and so I use the same pi here and here. So at the end of the Markov chain, this equation will be satisfied if there is convergence of the chain. And it turns out that the sufficient conditions for convergence are things that are very easy, like you need the sigma to be full rank and mu to project back into some bounded region. So there's a sort of funny interpretation of this, which is that so this is the density that the model is actually sampling from. And one way to think about it is it's like a kind of mixture of Gaussians. So these are the Gaussians for each component. There's one component, one x tilde, for each possible point in space. So it's like an uncountable Gaussian mixture. And the weights of each component are the density itself. So wrap your mind around that, and then let's see something more basic, which is whether this density that we're sampling from in the end using this procedure has anything to do with the original distribution from which the data was coming from. I mean, the whole objective of machine learning is to come up with a model or some representation of the distribution of the data that's somehow faithful to the unknown original distribution from which it comes from. So for this to make some sense, in statistical learning theory, people have invented the notion of consistency. So you'd like that in at least the limit case where you have lots and lots of data and sort of infinite computation power, you'd like your model to converge to the right density. So let's see what is going on in our situation. So to analyze in a kind of non-parametric way just what our training criterion is doing and how it relates to this density that we're sampling from at the end. What we're going to do is we're going to consider every possible point x0 in our space and draw a little ball of size delta around x0 and consider the density in that ball. So that's the density p, and then we multiply by the indicator of being in the ball and normalize, and we get this p tilde, which is the density around x0. So the reason we're going to do that is we are going to show that our training criterion of reconstruction error with some contractive regularization amounts to estimating local moments like the mean and the covariance in each possible ball at every possible location. And so what we do is we are going to consider these moments. So pi here is this distribution from which we're sampling with our Markov chain. And so that's the local moment according to the distribution that we're sampling from using this Markov chain. Then the way we get that is we plug in our sort of asymptotic distribution, which we had before, which is this mixture of uncountable sort of integral of Gaussians. And we replace p by this p, and in this expectation. And it turns out that what we get at the end is that so the local mean of the distribution from which we sample with our algorithm happens to be an average of the mu of x that we used in our sampler. So if our sampler used some particular mu, essentially the distribution that we're going to sample from is going to have local means, which are these like local moments, which are essentially those mu's up to a local averaging. So this is averaging in the ball, basically, of the mu's. Okay, so that's interesting and sort of intuitively satisfying. It says that there's an immediate relationship between the means that we're sampling from in our sampling algorithm and the local statistics, the local means associated with the density that we're constructing with our Markov chain. And furthermore, remember that this averaging here is averaging in these balls, and in some there's an approximation here which depends on the size sigma of our steps. So these steps control the quality of the approximation over which we are sort of locally smoothing the moments. Okay, so this just establishes a relationship between the density that we're implicitly sampling from using our Markov chain and what we use as a mu for our Markov chain. Now let's connect that to the data, which is the thing that really matters. So that's the consistency part. All right, so we're going to minimize reconstruction error. This is this, plus a contractive penalty, this thing. So the Jacobian of reconstruction with respect to the input. And here we're integrating over all the x0s. So we're going to introduce these little balls I was talking about by adding an extra integral over x. So let's make these balls very small, and then these little balls are like just like Dirac's. So in the limit where the balls become 0 is the same thing as this. We're just adding this extra variable here, and now we can rewrite this integral. And the way we're going to rewrite it is, first of all, we're going to consider what happens around each point x0. We're going to say the reconstruction at x, which is now a neighbor of x0, is the reconstruction at the middle of the ball, plus the Jacobian times x minus x0. And we're going to ignore higher order terms because x is very close to x0. So in a sense, what we're going to do here is just do a local parametrization around x0, where we're going to have 2 degrees of freedom, which is the reconstruction at x0 and the Jacobian matrix at x0. So in a sense, we're going to be completely non-parametric. We're going to allow our learning algorithm to have the freedom to choose at every point the value of the reconstruction function. So that's totally non-parametric. And we also allow it to choose the local Jacobian, which is like the local manifold tangents. And the reason we're going to do that is we're going to plug that definition in this, and we're going to solve and find what is the optimal R0 and the optimal J0, and we're going to find the answers that I was telling you about before, that R0 is going to be the local mean and J0 is going to be the local covariance. So it turns out that this integral you can write as an integral over the different x0 of some local integral. So in other words, we have like all of the x0s, all the possible points, and around each of them we have like a local integral which is in the ball. So this is the integral in the ball. So now we have in a little neighborhood x minus the local linear approximation of the reconstruction plus our regularization penalties. And the reason we kept this first order term is that it shows up in our regularizer, so we need to keep it. And now we minimize this, set the derivatives to 0, and essentially we get the things I was claiming, that the sort of non-parametric asymptotic optimal reconstruction is the local mean, and the optimal sort of tangent plane, or the matrix, the Jacobian matrix, is proportional to the local covariance. So what all this math really says is that if we train by minimizing reconstruction error plus a contractive penalty on the reconstruction, then the best thing that you could hope for, if you have infinite amount of data, infinite amount of capacity, is converging to a function whose value is going to be the local mean and whose first derivative Jacobian matrix is going to be the local covariance. So we know now that when we minimize reconstruction error, we're estimating the local first and second moments of the density. Okay, so now this is interesting, and it gives us sort of another principle for learning, which is different from maximum likelihood, which is a kind of moment matching. In a sense, we can think of what happens when we minimize reconstruction error as we are locally matching the moment of the distribution. And I have other things related not only to the first local moments, but also to the first and second derivatives. We talked before about the first derivative, but there's also a connection with the second derivative of the density. So we don't have an explicit representation of the density, but we have an implicit one because we can obtain samples from the estimated density. And we know that if we run this chain, the samples we get asymptotically are from the estimated density. Now, if we really insist on having an analytic formulation for the estimated density, we can do it, in principle at least. I haven't actually done it. But what you would do is, if you have an energy function, you would just, because of the connection with the first derivative of the density, if we have an energy function, we could compute its derivative. So energy is a scalar, x is a vector. Derivative of energy with respect to x is called the score. It's a vector function of x. And we can just declare that score, the derivative of the energy, to be the reconstruction minus x. And so now that gives us a reconstruction. So if we have an energy function, there is a reconstruction function that corresponds to it. Now, if you give me any energy-based model that has like a free energy, then I can convert it into a reconstruction function. And once I have a reconstruction function, I can plug the reconstruction error as a training criterion along with a contractive regularizer. So if you start from a model that has an energy, you can train it by reconstruction error plus regularization, and you'll have, at the end of the day, not only a way to sample from the model, but an explicit analytic formulation of the density if you really insist on having one. Okay, so this is pretty recent work, and there are lots of open questions, like, okay, so this analysis is non-parametric and asymptotic. What would happen if we consider the parametric non-asymptotic setting, which is the real setting where we do things? What happens if you actually train energy-based models where you have an explicit energy using this formulation? We haven't tried it. And there are questions like, there are some subtle differences between the way we've trained contractive autoencoders and denoising autoencoders. So this one is contractive in the reconstruction. This one is contractive on the encoder. Somehow we seem to get better results using the contractive one, but we don't really understand. All our math is really for this guy. So we still have to understand better subtleties there. All right, so let's move to kind of another part of my presentation. Maybe you have some questions about this before I move on? Yes?
In the sampling, you basically move along the manifold.
I didn't hear well.
During the sampling, you basically move along the manifold. How do you move from one manifold to the other?
I don't know, but it works.
So you basically just introduce
Let me show you some things.
arrow which is big enough to move from one
Yeah, somehow does that. You can see, I mean, some kind of 5, 3, 8, 2. It jumps from manifold to manifold. So I think what happens is at some point you add noise, which moves so far away from the current manifold that when you do the reconstruction, it jumps to another manifold, right? Basically, there are two steps, right? Add noise, jump to the manifold with the reconstruction. So when the noise is sort of pushing you too far from the manifold, at the next reconstruction step, you move back to something that may be a different class.
But then you have no guarantee that you will eventually visit all the manifolds. You have to set an error which might be...
Well, there's never any guarantee that you will visit all the manifolds. But actually, I'll say a few words about that shortly. It's a problem with every MCMC method that it's hard to mix between modes, places of high density, which are really manifolds. But that's a very important and interesting question. I'll come back to that. All right. Yeah?
In those pictures, how many steps are between each?
One.
One.
So it mixes really fast. Yeah. Okay. So now let's move into some sort of easier material, less math, and more practical. I wrote this, this paper, which will be a chapter of a book called Practical Recommendations for Gradient-Based Training of Deep Architectures. You can find it on my webpage, and it's sort of highlighted in the first page on the left-hand side, along with the pointer to the slides for the summer school. And if you want to actually use these things in practice, I really encourage you to read that, which is a bunch of basically recipes. And it's going to be part of a book about the same subject from different authors, including Jeff and hopefully Jan, if he manages to finish his chapter. In time, I mean. The deadline was like 2 months ago. Oh no, 1 month ago. Okay, so it talks about the things you already know, unsupervised pre-training, stochastic gradient descent, sort of general stuff about that, and the idea of learning rates. I guess the main part of the chapter is talking about the hyperparameters and some recipes to set them. The learning rate schedule, early stopping is a really nice trick. Mini batches today, when you use GPUs or regular CPUs, using mini batches, maybe of size 20 or 100 or even more, can be computationally advantageous. How to initialize parameters. I'll talk about some of these things in the next few slides. Number of heating units. So actually, the number of heating units is practically not important from the point of view of generalization. The more the better, at least when you do unsupervised learning or unsupervised pre-training. So it's more like how much can you afford given your computation budget and time that you're willing to wait. Sort of standard regularization of the parameters, regularization of the activations like sparsity or contractive penalizations. Ideas about how you can debug these things. Debugging is really important in real life. So a few ideas about how to do that. And maybe one of the most important pieces, and I have one slide about that later, what you can do to make the search for hyperparameter configurations less painful and more automatic. So I suppose you've seen already a lot about stochastic gradient descent, so I'm gonna skip that. The only thing I would say is don't use regular gradient descent, never ever. Just use stochastic gradient descent if you're gonna use gradient descent at all. Learning rates, so if you use gradient descent, learning rates are really important. It's the single most important hyperparameter when you use any kind of neural net or deep learning or things like that is the learning rate. And you might have a whole learning rate schedule. And one way to set the schedule is in this formula I'm going to explain. So in general, you can have a constant learning rate, which is the same for all parameters and the same over all iterations. And that's, if you're like in a hurry to get some results, that's the very easy, simple thing to do, and you have just one hyperparameter. Or you can have some heuristic to change the learning rates depending on things like how many weights come into each unit. Or you may have smarter heuristics like those that Ian is working on these days. And then you can also change the learning rate over iterations. For example, you've seen, I'm sure, the math saying, something like decreasing in 1 over the number of iterations is a good idea. So here's a particular recipe we use. Epsilon 0 is your initial learning rate. Epsilon t is the learning rate at iteration t. And then tau here is a time scale, a time constant. So when t is less than tau, you get a constant learning rate. And when t is 2 tau, you get the initial learning rate divided by 2. When t is 5 tau, you get the initial learning rate divided by 5. So it goes as 1 over t, and tau controls the scale of that. It's a nice little formula. Early stopping, if you do anything with many iterative optimization algorithms, and in particular stochastic gradient descent, early stopping is really a nice thing you should always use, because it's a real free lunch. It's one of these hyperparameters that is set for free. So the hyperparameter that you're setting for free here is the number of training iterations. And the way you're getting that is you're doing more iterations than necessary, but keeping track of which one gave you the best validation error or the best some estimation of test error. So it's very easy. Just monitor error during the way and keep track of the best parameters that you found along the way. And then you have some heuristics to decide actually whether you want to continue and how much, which means you don't even have to decide ahead of time how long you want to train. So that's very nice. So I have a little digression about long-term dependencies here, which is connected to a new trick that I'll tell you about on the next slide. So in a previous life, I did some work on recurrent neural nets, which are coming back as a very important method for training complicated nonlinear functions that deal with sequences. But some of the ideas apply to deep nets. Recurrent nets are basically very deep nets. I showed that picture before, right? So you have a sequence of inputs, and you have this sequence of hidden activations, and you obtain the tth one from the previous one using maybe sigmoid of some weight times these guys plus some weights times these guys, and so on. And the problem that I worked on some 20 years ago is that training recurrent nets is difficult, and the sort of main reason why it's difficult is because you have all of these nonlinearities composed with each other. So this is meant to be the state at time t plus 1 is a nonlinear function of the state at time t, which is a nonlinear function of the state at time t minus 1, and so on. When you compose all of these nonlinearities, you get something highly nonlinear, and you're trying to optimize this highly nonlinear thing is very difficult. So in a sense, it's the same thing when you do deep nets. And one way to see why it's difficult is to look at the gradient. So the gradient on the state at time t is the multiplication of all these derivative matrices, so these Jacobians. So this one is a vector, but all the others are matrices. Which says how the state at time t influences the state at time t plus 1. And the problem is when you multiply a bunch of matrices together, and it turns out these matrices are kind of similar to each other in addition, then what happens is, it's like you multiply a bunch of numbers together, right? If the numbers are greater than 1, then they become large very quickly, and if the numbers are less than 1, then they become very small very quickly, and that's bad in both cases. So because these are gradients, you may get gradients to explode, or you may get gradients to vanish and shrink. And the reason I call this the problem of long-term dependencies is that when they shrink, the long-term effects become exponentially smaller than the short-term effects. So if you consider the effect on a t which is close to the final one, then this is a short-term effect, and it's very easy to learn, and it dominates the gradient, whereas long-term effects kind of exponentially weaker and hard to learn from. So that was the work I did in the 90s, summary of it. And it turns out that there's a very nice trick introduced by Tomasz Mikolov. We should have a paper on that shortly, which is the following. And it deals with the first problem, the gradients exploding. In my paper, I was mostly focusing on, okay, this is a big problem because the gradient's vanishing, but actually in practice, this one is actually also present, and we hadn't paid enough attention to it. And what he suggested is just, okay, so when the norm of the gradient is above some maximum value, just ignore the norm, clip the norm. If the norm is greater than 2.5, let's say it's 2.5. So it's kind of a hack, but it works. And it makes a big difference, and because of this trick and other sort of nice tricks, some of which I'll talk about Friday, he was able to get state-of-the-art performance on language modeling tasks, beating the state-of-the-art in text compression, language modeling, speech recognition. The language modeling part of speech recognition, but measuring word error rates. So just, sometimes just a few well-chosen tricks can, make you famous. So let's talk about another practical concern, initialization. So we have this paper, it's not cited here, I guess. So it's, I should have put it's a paper with Gloro, one of my students, AI Stats 2010, where we end up proposing an initialization recipe for deep neural nets, in which we say, okay, sample from a uniform between minus something and plus something, and the something depends on the size of the layer before and the size of the layer after, right? So we're looking at the weight matrix between, layer I and layer I plus 1. This is the size of the layer I and size of layer I plus 1. And I'm not going to go through the math of that, but the gist of it is we are trying to make the Jacobian matrices, again, these Jacobian matrices are coming back, trying to make them as variance preserving as possible. And what that means, variance preserving, is basically over the kinds of vectors that it sees, the norm of the vectors are kept the same. In other words, the singular values are close to 1, or the maximum singular value is close to 1, so that it tends to propagate information both ways, forward and backward, and neither shrink nor expand too much the size of the vectors. So if the weights are too large, you can get expansion. If the weights are too small, you can get shrinking. And so this is like a good compromise to try to make them in between. And we've done experiments which you can check in the paper. Oh, actually, here's the sort of the reference. If you look at my list of papers, and we find the interesting finding. I'm not going to go through all of these things, but we tried all kinds of nonlinearities. But the important message is test error going down in terms of number of examples seen. So this is a convergence of test error. That using this initialization, which is a slight variation on things that others have been proposing before, we're able to train pretty deep supervised networks without any unsupervised pre-training, much better than was possible before. And we're almost reaching. So okay, this is with pre-training, and this is like a regular sigmoid net with supervised learning. And this guy here is using our initialization. So, it's like we've covered a good deal of the gap here just by being smart about initialization. Okay, there's another practical concern that I'll come back on Friday, which is that in many applications, you want to, with a neural net, in particular with autoencoders, your output space is large. So in particular, if your output space is your input space, and your input space is large, then your output space is large as well. And and that's very costly. So particular in sort of language modeling tasks or other tasks where your input is high dimensional and sparse, maybe your input space is 100 dimensional inputs. And if it's sparse, computing the encoder is cheap because let's say you have 100,000 dimensions here, but only 100 out of these are non-zero, then the actual number of computations you need to do to compute the code here is only 100. It's the number of non-zeros. You don't need to visit the zeros. You can be smart about that. It's just a sparse matrix vector operation. But when you want to reconstruct, you don't know which one is you have to reconstruct all of them. That's the loss is over all of them. And so that's going to be very, very expensive. So we proposed a trick, which is kind of derived from importance sampling, where we're going to compute the loss only on some subset of these, and using a proper weighing of the loss, the importance weights, we can make that computation very, very efficient and focus on the units which are most likely to have a large error, which is what you want. There are also, so this is ICML last year. Then there are all other ideas that I'll talk about next Friday. Also using some sampling ideas to avoid having to look at all the outputs. And also ideas based on decomposing probabilities in a hierarchy like this, so that you can, your output is now sort of sequential. You first predict categories and then you predict items within categories. And then sort of the total number of computations you need to do here would be square root of what you would have to do otherwise. I'll come back to that on Friday. Automatic differentiation. Okay, so I'm guessing that James Bergstra has talked about that. Now this, I don't know if James talked about this, but it's a really useful practical trick. If you have more than 2 hyperparameters, which is clearly the case for deep learning methods, it's kind of painful to explore this set of hyperparameters. Now, if you have a cluster of computers, you could imagine launching different configurations of your training jobs with different values of hyperparameters on your clusters, on your like 50 or 100 or 200 machines, 200 cores. But the usual way of doing it is having a grid. In other words, you take, say, 5 different values of learning rate and 10 different values of number of hidden units and 2 different types of initialization and 2 different types of nonlinearities and blah, blah, blah. And you take all of the cross product of these configurations, so that's the grid layout. And then for each of these configurations, the cross product of all the values, you launch a job. So you can see, first of all, that it still explodes in terms of number of computation, because you have an exponential number of jobs to launch with respect to the number of different hyperparameters you want to explore. Now, there's an alternative, which is this, where you're going to take each hyperparameter, and you're not going to discretize the values to large, to a small number of bins or something. You're going to keep them continuous, or keep them like number of hidden units as an integer. You don't have to choose, between 100 and 200. You can pick any number. You're going to separately sample each hyperparameter. So I'm going to, for example, the learning rate, let's say, I think it's between 0.1 and 0.0001. So I'm going to take the log of this, the log of that, and take a uniform between those 2 logs. And then, because the result is like a log of a learning rate, I take the exponential. It's just to be on the log scale rather than the original scale, because we know that like learning rate of 0.1 or learning rate of 0.2 is kind of very close, but between 0.1 and 0.01, there's a big difference. in terms of performance. So you want to be on a multiplicative scale. Anyways, you sample each hyperparameter separately. You do that, and then you get a configuration of hyperparameters. You launch that on your cluster, and you get one of these points. But you throw random darts in the space of configurations rather than the regular grid. And the advantage of that is that if there are some hyperparameters that are irrelevant or slightly irrelevant, then this is going to converge exponentially faster than this. And we've written a paper about that somewhere in JMLR, I think, this year, which explains this idea. But you can see it visually. Let's say that one of the hyperparameters was kind of useless. In other words, this is the profile of your, say, likelihood for different values of the hyperparameter. When you look in this direction or this direction, if you marginalize, you see that this hyperparameter basically has no effect, whereas this one has a peak here. So there's like basically the good value is around here. Turns out our grid was not fine enough, so we can't actually pick the right one. But if we throw random darts to the space of configurations, now the marginal distribution is much richer because we have a lot more different values for each of the hyperparameters, and we are maybe much more likely to find a good value. And because of that, you converge much faster. You need many fewer trials before you get a good answer. And then other advantages are things like, if some of the jobs fail, you just ignore them because they are IID. You don't care. If you want more jobs because you see that your error improves as you add more jobs, you can do that and you don't have to restart from scratch. A bunch of nice practical advantages. So very easy to do. Just one line to change in your code, and it converges much faster, and it allows you to almost automate the hyperparameter optimization thing. Okay, last part. Some questions and discussion items. So one of the first questions we looked at that was more of a scientific nature, trying to understand what is going on with these algorithms, was why is this unsupervised pre-training procedure that you've been hearing about working so well, or when it does. And so we had two hypotheses. Well, maybe it's a regularization effect, or maybe it has to do with local minima and optimization effect. So it turns out that both of these effects were there, but not exactly like we had thought about initially. So the reason there would be a regularization effect we've talked about already, because somehow we're assuming that representations that are good for P of x are in part good for P of y given x. And the experiments essentially validate that. And the optimization hypothesis, well, we thought maybe there are these local minima, and the unsupervised initialization gets you closer to local minima of the likelihood that you want to minimize. It turns out that it's not exactly what is going on. What happens is that the unsupervised initialization gets you better local minima of the generalization error of your supervised criterion. So it's not that it makes the optimization of the training error better, it makes the optimization of the generalization error better. This is really a subtle and important difference, which vanishes when you consider a very large number of examples, but it means it's connected to this regularization effect as well. Okay, now let me explain this very nice picture. So to try to understand what was going on in these networks with the unsupervised pre-training and with and without, and to study this story about local minima, we run a large series of experiments with hundreds of jobs, all the same except for random initialization. And we had two conditions, either with unsupervised pre-training or with supervised pre-training, either without unsupervised pre-training or with unsupervised pre-training. So each point here on this diagram represents one neural network in its supervised fine-tuning phase at a different stage of its training, at a different epoch. So the color represents sort of the age or the number of iterations. So they all start blue and they end up being red. Or if they start shorter, they end up being green. So like here, they all start in the same region in function space, and they move And then one of them goes like this and converges to a local minimum in function space. Now, how do we represent function space? First of all, we need to work in the space of functions and not in the space of parameters, because neural nets are not identifiable, so the same function can be represented by many different sets of parameters. So how do we work in function space? How do you visualize that? What you do is you do it non-parametrically. So what you say is, okay, I'm going to look at the output of the neural net on the test examples. So let's say I have 10,000 test examples. I just take all of the outputs over the 10,000 test examples, concatenate them in one huge vector. And you say, well, that vector is a proxy for the function computed by the neural net. And that's a very high dimensional vector. But I can use a nonlinear dimensionality reduction method like TSNE. It's not written here, but TSNE, invented by Jeff and one of his collaborators. And map that to 2 dimensions. And that's what you see here. So in other words, points that are close to each other compute something similar. Okay, so what we see is that different networks converge to different functions, and at some point during training, they're all in their own little world. And the final function here is different from this other network and this other network and so on, and they all go to a different place. There are no 2 different networks that went to the same place, even though we launched like hundreds of jobs, like 500 jobs. So that's interesting. Like imagine you throw darts, and they can fall into. No, you don't throw darts. You throw balls, right? And they can fall into little balls, little local minima. But every time you throw, it ends up in a different place. How many local minima do you think there were if none of them out of like 500 fell in the same place? I'm sure someone can do the computation. I didn't do it, but it would be fun to do it. Anyway, it's huge probably. So that means there's lots of local minima, but that's one conclusion. There's another conclusion, which is that these guys were without unsupervised pre-training, and these guys were with unsupervised pre-training. It says that, even if I launch 500 different times without unsupervised pre-training, I never find any of those guys anywhere close these guys. So actually, let me show you the next picture. So this is using another dimensionality reduction method called isomap, which tries to preserve distances in volume, even though it reduces to 2 dimensions. So it's more faithful to the geometry of function space. So what it says is they all start in this region. The ones without unsupervised pre-training go in some direction in function space, and then the ones with pre-training go in a totally orthogonal direction. That's what this means, really. It's like completely unrelated somehow. And not only that, these guys, they all go to very close to each other, whereas these guys, cover a much wider variance of functions. So that says that, well, that explains a little bit the fact that there's more error because there's more variance between these guys, and these guys are more consistent with each other. But also, like you could continue throwing these random initializations without pre-training, you'd never find those guys. So it's like the good solutions are not accessible by chance, basically. Okay.
This is closer to global minimum, or do you think the with pre-training?
Well, I have no idea where the global minimum is.
No, I mean, why should it pick one specific local minimum?
You mean why they all go to the same place? I think it's a matter of dynamics, right? So you have to think of the optimization procedure as a dynamical system. Stochastic one, because you have the initial noise and then you might have the sort of stochastic sampling noise. Yeah. And so depending on the quality of the dynamics, that will sort of define where they go, basically, even though there's noise. Yeah.
Would the same thing happen with the initialization you just mentioned, or using the square root of 6 over square root of 10 and so on?
I don't know. Why don't you try that?
So it's a comment on it's possible response to this question. Much of the difference between the different solutions you get is due to how the system breaks the symmetry between the various solutions it can get to, and so depending on your initial condition, the symmetry will be working in a random direction, which is why you're getting all those different solutions when you initialize randomly. But when you do the pre-training, that breaks the symmetry right there. So it constrains the system to one particular part of the parameter space, and basically they all go to the same local minimum.
Well, not quite, but
it's not quite the same minimum, but it's the same kind of Bassin of attractor.
Right.
You know, there's a bunch of similar attractors there.
You had another question.
So what can you say from the bias variance dilemma perspective here?
From a bias variance, oh well, it's pretty obvious that the variance is bigger, and I mean without pre-training, without unsupervised pre-training, and well, the bias is, what can I say about the bias? I mean, it's probably about the same for both. So one sort of indication of bias is training error, and it's kind of comparable, or in fact, you get slightly lower training error with these guys on MNIST. On which this was run. But you get a better trade-off using unsupervised pre-training. Yeah?
So if breaking the symmetry is really the big thing to take away from this, then I guess this is kind of independent.
It's not any breaking of the symmetry, right? Some breaking of the symmetries are better than others. Otherwise, some of the random initialization would also do a good job.
I guess the question I'm really trying to get at is, these effects are largely independent of both architecture and data then, right?
I don't know. I do think it's true, but this is one experiment on one data set, one architecture.
What for each?
Huh?
What data, what architecture?
This has been done like 4 or 5 years ago, and that was on MNIST, and straight sort of fully connected feed-forward with denoising autoencoders or RBMs. Actually, we tried both RBMs and denoising autoencoders, and they do the same thing. But I suspect it's going to be true over a much larger range of things. But I think it would be good to replicate these kinds of results now with the different algorithms we have and more data sets. Yeah?
If it's really a function of the dynamics of the input,
Yeah.
so what if you like...
the dynamics of training.
Yeah, exactly.
Yeah.
So what if you cross-validated? So say you supervise unsupervised pre-training on like cross-validated input, do you get the same sort of...
I don't understand what is cross-validated inputs.
You pull out data, like they don't all see the exact same.
Oh yeah, I don't think it's going to be really different. So we've tried that kind of thing. Remember I had a picture with the effect of early examples. So in that case, we switched in and out, examples. So we changed the examples, and the quality of the functions was the same at the end of the day, right? So it's not very sensitive to the sampling of examples. It's something more basic about the dynamics that comes from the distribution, the architecture, the training criterion, all of these things together. All right, if there, yeah?
I'm just wondering, what is the limitation in the training procedure that doesn't let the without pre-training one even randomly get into that area of the one with pre-training? There must be some sort of limitation.
Well, I don't know. I have some sort of very vague notions like, if you learn a good representation, then you start off in a better region of parameter space. But
right, that would explain why most of them are in the good space.
Right.
But shouldn't randomly you be able to get it?
No, but the thing, so what this tells me is that the good initialization occupies a tiny volume in parameter space. So random initialization, are very unlikely, exponentially unlikely to find that place by chance. It's really a needle in a haystack. But if you change the dynamics properly by doing one of these tricks like unsupervised pre-training, then you can get a chance to be there. All right. So I guess I'm going to say a few words about inference. There's one thing I want to say about inference, which is that we probably have no choice but doing some kind of approximate inference, at least if you want to stick to the probabilistic view of things. And the things that Jan talked about, that Arthur talked about, basically are learning models in which you not only model the data, but you make sure that your approximate inference is going to be doing a good job. There's also some work on deep Boltzmann machine that have this kind of flavor where you learn a predictor for your hidden units that is kind of fast. It doesn't need all the long iterations of sampling and relaxation. There is something very basic in many of the models that we are exploring, especially the Boltzmann machine types, which is this partition function we've been talking about. It's intractable because it needs to, look at all the configurations of inputs and hidden units. And we can use MCMC estimators for computing the derivative of Z with respect to the parameters, but they're not very satisfying, as I'll be, I guess, talking about Friday because time is flying out. And that's because of the presence of many modes in the distribution, and it's becoming hard to sample and go from mode to mode to cover all those modes, and that makes the training very difficult. So if we could avoid this problem of the gradient of the partition function during training, I think that would be really good. And score matching is one of the ways that have been proposed for that. There is a noise contrastive estimation and related methods that I'll maybe briefly mention. Pseudo-likelihood is a kind of an established method, but it has some problems. Ranking criteria I'll talk about on Friday. And autoencoders, basically the reconstruction error story I gave today is also an alternative. You don't actually have to have a partition function if you use autoencoders. Okay, so I guess I have to stop now, and I can take more questions